I'm Atli. I'll be talking about large-scale and distributed optimization today. And there will be kind of two portions to this talk. First, I'm just going to talk about efficient single GPU training, which is kind of what you need to understand in order to do large-scale training. It's just a lot more GPUs, but many of the same principles still apply. Then in the second part of the talk, I'm actually going to talk about distributed training and large-scale training for something like LLMs. Okay, so let's get into this. GPUs. GPUs are the hardware that we use to train our deep learning models. There are alternatives like TPUs, which Google uses, and there are various startups that have created other hardware accelerators. But in practice, most people use GPUs, and specifically NVIDIA GPUs, since other GPUs don't really have great support for deep learning still. The kind of typical GPU that I'm going to use as an example for this talk is this NVIDIA A100 GPU. It's a few years old by now, but it's widely available. So if you go to a cloud provider, you can probably get some of these. Like the performance of a single GPU is pretty high nowadays. Like this A100, for instance, can do 300 teraflops of operations per second. That's roughly 300 trillion operations per second in these specific floating point formats that we'll talk about later. Each GPU nowadays has lots of memory, like 80 gigs in this case. Relatively high memory bandwidth compared to like CPUs, meaning that you can read this memory relatively fast, but as we'll see later, still not that fast overall. 400 watts roughly, and if you wanted to buy one, it's roughly 20K, but you can rent them online for like maybe $1 an hour or so. Each GPU is essentially just a collection of a bunch of tiny cores that all work together to do operations in parallel. And GPUs are kind of specifically made for these like highly parallelizable workloads, like matrix multiplications, which make up our neural networks. So yeah, the bottlenecks for GPU training is essentially that like although you have plenty of compute and a decent amount of memory, the speed at which you can read the memory, although quite fast overall, is still quite small relative to the compute. So what that means essentially is that for every operation that you do on the cores, or for every load from memory, you want to do lots of operations on these elements that you loaded from memory. So for something like modern GPUs, you want to do roughly maybe like 100, 200 operations per memory access that you make. And if you're unable to kind of like sustain this, then your GPU is not going to be very highly utilized. So the sort of canonical examples that the GPUs are basically designed for nowadays is this like matrix multiplication. In matrix multiplication, you can reuse every sort of like scalar that you load in the matrix, because it's used for essentially like every row is sort of, you take the dot product with every column in the second matrix. So you reuse like this like one row that you load, you can reuse it many times and amortize these like memory accesses. GPUs are bad at like these element-wise operations, where you, for instance, if you're adding two matrices, each element that you load from memory is only used once, and then you have to write it back out into memory, which means that like the compute is essentially not utilized at all. And they're also bad if you do lots of small operations. So every operation that you launch on a GPU has some overhead. If you're launching small operations, this overhead will also be significant. So just kind of like the high level tips for good performance is to operate on large inputs. Like one way that you can change this in your model training is by using larger batch sizes. Fusing sort of like small and element-wise operations The sort of practical way nowadays would be something like torch.compile. And we'll see later an example of like how this can affect performance. And then another important aspect to consider is the CPU side. So if you're training, let's say some model, you typically have a data set. The data originally lies in like CPU memory. You have to get the data into GPU memory before you can train it. If you don't do this efficiently, then the CPU can actually be the bottleneck and your GPU is not doing anything. And we'll see some examples of this again later. Yeah, another thing sort of with like modern GPU training is that like we use lower precision numbers than you might expect if you're not familiar with this. Specifically for floating point numbers. So a computer represents like what we call like real numbers or rational numbers with floating point numbers. If you've taken some CS classes, you may be familiar with this, but essentially a floating point number is exactly what the scientific notion for decimal numbers is. So you represent the number kind of like this. You have a sign for the number. You have some sort of like a normalized number in the range from like 1 to 10 for decimal, from 0 to 1 for binary, and then you have some exponent here. Essentially, different number formats will have a different number of significant digits and a different range for this exponent. So some number formats cannot represent, for instance, like very large numbers or very small numbers, and other number formats cannot represent too many significant digits. This generally leads to kind of numerical approximation errors. And so if you take an example for some kind of artificial floating point format in decimal with 2 significant digits and like an exponent in this range here, if we like this number 10 divided by 3 cannot be represented exactly by the floating point numbers. So the closest representation would be the like 3.3. And if we add 3 of these together, we get 9.9, which we can also represent, which is not equal to 10. So you get rounding errors. Another issue is called swamping, which basically means that if you have a large number and you add a small number to it, unless you have enough significant digits, like the result will be the same as the large number. So you can't represent this like small change in the value. So if again we do something like this for our like hypothetical number format, like this with 2 significant digits, once we hit 99 here, which we can represent, and we can go to 100, but like 100, if we add 1 to 100, like we can no longer represent this change in the in this precision. So if we sum 1,000 numbers, like 1.0, we end up with 100. We do not end up with 1,000, called swamping. And then like underflow and overflow. So like this number here, we can't represent, it will represent the 0. And if we go above the maximum value, we get like infinities, which are also representable. But like the reason we do all of this is essentially like that it's much cheaper in hardware to operate on these smaller numbers. They just have fewer bits. It's simpler logic in hardware to do operations like multiplications, additions, and so on, which means in practice that you can just fit more sort of like cores on your chip and get more compute power this way. So in practice, we can see this with the A100 performance. If you're operating in what we call like float 32, which is kind of your standard like floating point format for computing, and is represented in hardware like this. You have 1 bit for the sign, you have 8 bits for the exponent, and then like this fraction or mantissa, which are kind of like significant digits in binary. You have 23 of them. But if you use this, which is kind of what you would get by default, unless you do something about it, you can only get 20 teraflops. compared to if you use like these lower precision formats, you can get 300. So like 15 times more just by switching to a low precision format. And if you do have these modern GPUs, you should probably be using some sort of mixed precision or like lower precision training if you care about this. And yeah, in practice, we get errors if we use like these lower precision formats without basically thinking about it. So like the field has kind of like developed these tricks with called mixed precision training, which combines these different formats. So some operations are done in low precision, other operations are done in high precision. So we're kind of using low precision where we can, but specifically doing the sort of like difficult operations in high precision to avoid these issues. And nowadays it mostly just like works out of the box. So this is how you would implement this in something like PyTorch. So the code here, it starts by just creating some model. We don't care, it's some model function and an optimizer. And then the difference from maybe standard training is that we use these like scaling contexts. And here we can either like enable or disable this. It is good if you want to be able to run your code in either like high precision or mixed precision. So if this is false, it simply doesn't do anything. But what we need to do is that we kind of wrap our forward pass into this context manager shown here, where we specify the D type that we want to use. And again, this is either enabled or disabled. So we do the forward pass. Then when we do the backwards pass, we wrap the loss first inside of this scaling thing. And this is actually only needed for float 16. So if you use bfloat 16, you don't need to do it. So essentially, the scaler here is only technically required for certain formats, not other ones. But I just recommend having it in there, especially since like some GPUs only support, let's say, float 16. Newer GPUs also support bfloat 16. If you have to choose between these two, we typically go for like bfloat now because they are simpler to use. You don't have to do this here. And then, yeah, the rest is essentially the same as before.
So can I just ask a question?
Yeah.
So if you're saying that using the scaler, the grad scaler, is if it's not required, it doesn't break it doesn't harm anything, it doesn't slow things down.
Yes, it essentially shouldn't do anything. I believe if
so if you have old or limited hardware, then you should use it. And if you have better hardware, then it won't be less efficient after.
Yeah, so if you have something like a V100, which only supports float 16, which is like these are like 6 years old now or something, then you need to use this. I'm not 100% sure if this, if you should manually disable this if you're using, let's say, like bfloat. I would have to look at the implementation, but in practice, what this does is that it will detect these kind of like underflows that happen during the backwards pass, underflows and overflows, and so basically like the model will try to back propagate and see if you get like infinities or nines at some point, and it will change the scaling, which shifts the exponent of these numbers, and it'll just do this. But the issue with or the nice thing about bfloat is that the exponent range is the same as float 32. You never run into this issue there. Okay, and yeah, just here an extra note. In practice, there are a few different types of mixed precision training, like this thing that you get by default. Basically, it doesn't touch the optimizer at all. Whereas there are some like fancier and more brittle approaches that also change the optimizer states. So here we use float 32 for everything in the optimizer, all the weights and so on. They work exactly the same. but some people like to push this down to lower precision formats as well. But this is not what is being done here. Okay, yes. I basically either works. If you really do the scaling thing here, like either one is going to work in practice. Most people don't like this too much and would prefer just to use bfloat because this just is an unnecessarily maybe like complication. But the trade-off between float 16 and bfloat is essentially float 16 has more mantissa bits. It's more precise in the precision, but it has a smaller exponent range. If you do this scaling here, like the exponent range shouldn't matter too much. So yeah, but if I'm training, I personally use bfloat 16 unless it's not an option. So older hardware. Yes, TensorFlow 32 is it's kind of like an automatic way of getting better performance without going to like these low precision formats. So modern GPUs, they will actually kind of they can cheat on these like matrix multiplications, for instance. So instead of like actually doing them in float 32, they will do it in a lower precision behind the scenes, and then just like give you a result that kind of looks similar to what you get for the float 32. I'll show this in the tutorial as well. If you just want to use this TensorFlow 32, you don't need to do anything. Like, except just somewhere like at the start of your code, you should do something like this. Just enable this, because otherwise it depends on kind of like which container you're using. If you're using a container from NVIDIA, they will do this for you automatically. If you're using the default PyTorch, they will probably not do it.
Anywhere, but for any program, we can always use TF32 and
That's the claim from NVIDIA when they sort of like released this TensorFlow 32 format. The claim is that like it has sufficient mantissa bits to be like not an issue while keeping the exponent range the same as float 32. So, but you typically lose a bit of performance. So like TF32 is actually it's stored as a 32 bit number. So it's more expensive to load, and I think the course also you lose like a factor of 2 or something when you do the multiplications versus using the low precision formats. This TensorFlow 32 is only available on like more recent GPUs like A100s and later, essentially. Okay, so we had a short tutorial on this just to illustrate some of these concepts. Here I should have a yeah. I mean, not really. Sorry? Not really.
Control and plus zoom in, control minus zoom out.
So I'm on a Mac, but either command or control like doesn't seem to do anything. I can so it's really no. Maybe it's just not. Yeah, I think there might just be some issue with this. Since you would expect this to at least either one of these, but okay. I'll just try to zoom in on the code or or results. Yeah. So and NVIDIA SMI, I'm just kind of checking the status of the GPU. Here I have an A100, which should be so shown here, has the 80 gigs of memory that we talked about before. Okay, so by default, like even though you have a GPU in PyTorch, you're not using the GPU unless you specifically tell PyTorch to use the GPU. So some people make this mistake. Essentially, if you don't specify anything, your tensors will be created on the CPU, and if you do operations on them, no GPU is used. You can move a CPU tensor to the GPU by either of these two methods. If you have multiple GPUs available in your environment, you can differentiate between them with this number here following the CUDA. And you can just create tensors on the GPU. And I recommend doing this unless there is a reason, not to. By default, if you don't do anything, your tensors will be created in float 32. If it's a floating point kind of functions like zeros, or int 64, if it's like what we call like an integer function, like an a range. So round n, again, you would expect a float from it. You get float 32. We can change this by specifying a d type when we create the tensors. If you know that you want to use some other format, I generally recommend doing this on creation. It's going to be more efficient than later converting it. What you can do with these typecasts. So you create it in float 16. When you print this, it's going to be bfloat 16. There are lots of different types. Like most of these, you want to use. So some of this maybe for some sort of like image data that you load on the GPU that you eventually like change to floats. But this is mostly what we sort of care about for neural network training. Here I'm going to try to kind of illustrate some of these precision issues. So here there's just one way of creating a tensor with a given value. But here it's bfloat 16. I asked for the value 257. This value is not representable in bfloat 16, so it's already rounded to the nearest value, which is 256. So yeah, not even like relatively small integers can be represented precisely in bfloat, which is good to know. And here, if you have lots of digits, basically, it's getting the here roughly the fourth digit incorrect. The exponent range, float 16 has a limited range, as we discussed before. So 1e5 is not representable, goes to infinity. 1e minus 8, too low, represented as a 0. Here, like this swamping issue that I discussed, due to some implementation sort of details, you may sometimes see swamping and sometimes not. One way to see it for sure is just to force this operation to happen like one by one. So here I create two bfloat numbers. One is 1 and the other one is 0. We are going to sum up a many times. So we do this 500 times, but we end up with a value of 256 for the reasons I talked about before. Essentially, 257 is not representable in bfloat. So if you add 256 plus 1, it's going to be 257, which is rounded back down to 256, and this saturates this accumulation. If if you do the same thing in a different way, by just creating a tensor of ones of 500 values, and then we add PyTorch to sum, you actually get the value of 500, which happens to be representable in bfloat 16. But the way that PyTorch achieves this is that it either does the internal accumulation in float 32. So essentially, if we were to write code like this, here B would actually be a float 32 value that PyTorch is accumulating into, or it's doing the sum in kind of like a tree manner. And if you do the sum in this kind of like these like tree reduction algorithms, then in practice you're not adding the small values to large values. You start by adding like two small values, and you get a bigger value, and you only add this bigger value to another bigger value that you get from like a different portion in the tree, and so you can reduce it like this. Yep.
So say 157 is not represented by what 500 is represented.
Yes. So the reason 257 cannot be represented is that there are not enough significant digits to represent it, whereas 500 is representable just with essentially like lower precision. So if you do this, so by just changing this exponent here, you can represent both small values and large values. But the smallest increase that you can get at larger values is larger in absolute terms than at the smaller values. The same, you can get the same relative increase. I don't know if this is making sense, but if yeah.
Yeah, so 500 could go to 2 digits, 510, 520, 530, but you can't do 531 or 251.
Yes.
Although you had 256, so I don't quite understand where it's.
So, yeah, it's base 2 for this. So 256 above 256, instead of like adding ones, which we can do below it, we need to add twos. So if I do like 256 plus 2, it's going to be 258. Oh, yeah. So like the precision increased because you jumped up like an exponent here. Okay. And then I also want to show some of these performance aspects. So here I've created a function that is essentially going to time different GPU operations, and the details of this don't really matter too much. But one thing to know in general is that the GPU typically runs kind of asynchronously from the CPU. So if you just tell PyTorch to do like a bunch of GPU operations, it'll actually kind of queue it up, and the CPU can kind of like, you know, continue on in the code, and the GPU will just like catch up when, you know, when possible. So to get actual time measurements on a GPU, you have to use some tricks. You either have to set a synchronization point between the CPU and the GPU, or you can insert events that on the GPU that will record the time difference. But it's a common mistake when people measure performance is to kind of not do this, and you're trying to measure some big op, and you get basically, it takes no time because the CPU just jumped to the next line, and there, you know, the GPU hadn't actually finished doing the operations that you're trying to measure. Okay. Then here I'm just going to show the effects of doing basically matrix multiplications of different dimensions, and I'm going to measure like how many operations the GPU is able to do per second. So how many, like, you know, scalar addition, scalar multiplications, which make up these big matrix multiplications, is it able to do per second? Basically, how many flops per second are you actually achieving? And we're going to do this in a bunch of different formats. And if we do this, we will end up with something like this, which kind of demonstrates that you want to use lower precision formats. So here, the two high precision formats, float 64 and float 32, you can see that basically, you know, across different matrix dimensions, you your performance is relatively low compared to these low precision formats, and the difference is quite high, like maybe close to this like 15x that we saw before. T-float 32 is somewhere in the middle. You're getting like roughly half the precision, half the throughput of float 16 or B float 16. And in general, you can see basically, unless you have large matrices, none of this matters too much. If you're doing operations on small matrices here, like the dimensions would be what, like 64 by 64. Basically, it doesn't matter what format you're doing, it's going to be super slow anyway. But if you go to here, you know, here the dimensions are like 1000. Up here, I guess you're like, you know, 16K, 8K, 4K roughly. There you're actually getting roughly the full utilization of the GPU. Okay, in general, this maybe doesn't matter directly to you, because in practice, the thing that you can affect is the batch size. Typically your model is fixed, but larger models, generally you get better utilization from. But we can do a very similar measurement for batch size. So here we are multiplying a matrix that is 500 by 512 by 512 to batch sizes of different dimensions. So a matrix that is 512 by the batch size. And again, we're just measuring the throughput, and we can see that, like, you know, until your batch size is reaching roughly like maybe like 1000 or so, your utilization is quite low. So to really get the throughput of this GPU, you should be using batch sizes of like 1000 plus for these dimensions. Here we're gonna compare a memory heavy operation, sorry, a compute heavy operation like matrix multiplication to a low compute operation like addition. And so in matrix multiplication, every element that you load through memory, you can use multiple times. For addition, only once. So if you measure, like, you know, how many operations per second the GPU is doing, you can see this like huge gap here of like roughly this factor of like 100-ish that we talked about before. So GPUs are really only good at compute heavy operations like matrix multiplications. Something like additions, they're actually not that fast in comparison. Then, yeah, final thing I want to show is just data loading. Okay, the details here of the data set don't matter too much. I'm just creating some random data on the CPU and making the CPU do a little bit of work. So it's not only like allocating like something in memory. This maybe simulates more, you know, what would happen if you wanted to do some sort of image decoding or something. So the CPU has to do a little bit of work to get the data into a format that you can use on the GPU. And this is just some random code to simulate this. Okay, so some, you know, neural network like operations here that we're going to make the GPU do. And then we are going to essentially do like one epoch of this. So we are going to create a data set with this. We're going to move the data to the GPU, to the operations, go through like one epoch, one pass through the data set. And so to do this, you create a data loader, which I hope you've seen before. And yeah, okay, for the data loader, you can specify a number of workers. I think by default it is 0. And also what this means is that, like, you have the main process, the same process that is like telling the GPU what to do, and now this process is going to have to do all the data decoding. But you can also do this this sort of process parallelism on the CPU. So you can create new processes and make those processes do all the data loading work, while the main process will just do, you know, like the sort of like the high level GPU stuff. So keeping the GPU doing things. And in general, if you're working with like real things, you'll see like performance difference between these two. And there is one other sort of like detail about how you move the memory from CPU to GPU, so that you typically want to pin the memory. Pinning the memory is like an operating system thing. But what it means is essentially that the memory will not be pageable. And what this means is that the memory will have a fixed address. Like this data will have a fixed address in memory, meaning the GPU can directly fetch it without having to go through the CPU. It just speeds things up a little bit. And if you look at this, we can see that like if we use no parallelism for the data loader, you take roughly like 8 seconds per epoch. If you use multiple workers, we can cut this in roughly half and slightly more with pinned memory. In general, this is something I just recommend doing for your tasks. Just kind of like quickly check whether, like the data loading is actually limiting the throughput of your training, because it happens quite a bit in practice. And one way to check this is basically just to eliminate the GPU ops. So here, okay, it takes it takes 8 seconds. Let's see if I can do this. So in practice, what you might do, so this is just like commenting this out. So now we only move the data to the GPU. We don't do anything with it. We'll see like how fast the data loader can actually get the memory, get the data to the GPU. You want this number that you'll get here to be significantly lower than the time it takes without without any so if you do this, you want the number to be significantly lower than if you are actually doing work on it. And here, even with 4 workers, it is not that much lower. So we can kind of see that like yeah, out of these 8 seconds, like 6 were roughly just like the data loading. So the GPU is actually only doing something like 25% of the time. Here, it's honestly not much better. So you need more workers. But actually, one nice thing about this is that this can kind of happen in parallel. So even if this is on the same order, maybe your GPU can still be actually doing things behind the scenes. But in practice, you would want these numbers to be lowered. You could use more workers. That'd be the easiest way to get this. Okay.
So if you do too much number of things, it will actually show.
Yes.
And then the process can die because if number doesn't get enough data, it will just crash.
Yeah, so good points from Peter. If you set this number too high, typically like higher than the number of like processors or cores that you have on your CPU, you'll stop getting a benefit. And especially like if you're loading big batches with lots of workers, sometimes you run out of memory because each worker will have to allocate some memory, and then yeah, things will just crash for you.
For creation and process is not always higher than for actually doing stuff with one worker, then it's better to use like small number of workers.
Yeah, it'll depend on the workload a little bit. If you're doing something that is actually like CPU bound by compute, you want to use roughly the same number of workers as you do have like cores available, which is just going to give you like optimal utilization of the CPU compute. If you're in the end bound by something like CPU, like memory bandwidth or something like this, okay, not necessarily. But okay, maybe the best example of this is image loading. there you have to do maybe some like JPEG decoding or something like that. That is actually a compute heavy operation. And then, yeah, you want to use roughly number of workers equal to the number of cores that you have.
The second remark is that instead of committing the code, we can use NVIDIA SME and choose visualization. The visualization of around 100 smaller.
Yes, so like the comment was that you can use this like NVIDIA SMI that we showed here to roughly get some sort of utilization here. It's a good kind of like first step, but in practice, even if you're not, you know, bound by data, this number can be lower than 100%. And also, even if it's 100%, doesn't mean that the GPU is being utilized like efficiently. It just means it's doing like some things all the time. So it's not going to give you actually like, you know, this is more like utilization in terms of time, not like in terms of like throughput.
Yeah, but if it's used all the time, it doesn't mean that we don't have a bottleneck in data load. So
yes,
every time we use the batch, we process it, and the GPU processes everything all the time. So
yeah. I think, yeah, it'll give you an idea. It's just like not a, it can also be misleading in some cases, I guess. So this was that. Then, okay, what are we doing in practice on a single GPU? We're using mini batch parallelism, right? We don't use batch as a one, because as we saw, you know, that's going to be very computationally inefficient for the GPU. You're not going to be utilizing it. So larger batch sizes in practice. So yeah, the matrix multiplications become larger, allowing for more data reuse. You take fewer optimization steps. Sometimes, especially with like older versions of PyTorch, the optimizer step can be quite heavy because it involves like lots of these like little operations where you're taking like every parameter in your model and you're adding something to it. Maybe you're doing several steps if you're using something like Atom. Nowadays, like these optimizers in PyTorch are actually fused. So it'll just merge everything into like a few kernel launches, and it's much faster than it used to be. But you'll also have fewer kernel launches, like I discussed before. So it's both the dimension of the matrices and it's just fewer operations overall, which is lower overhead. This is the classical recommendation that most people still give, is like just figure out like the largest batch that fits on your GPU and use that. But this is actually not necessarily the optimal thing to do anymore. And the reason is that like larger batch sizes in terms of optimization only help you so much. Basically, there's a limit to like how large your batch size can be before you stop seeing optimization benefits from it. And this can be measured in practice just for different tasks. So here we have like a very small network. It's a ResNet 8 on CIFAR 10. And this is from a paper that kind of like measures this, but they essentially just, for different batch sizes, they will find some optimal hyperparameters by just, you know, trying like hundreds of combinations and figure out a good one. And they're measuring how many steps do you need to take before you reach a certain loss. And then here on the x-axis, the batch size is increasing. And on the y-axis, the number of steps that you require is going down. And if you think about it, you roughly want to be efficient, you roughly want the number of steps times the batch size to be a constant. And this is what is shown on this like dotted line here. And when this is a constant, it means that like for training, you're seeing the same number of like samples. You're computing the same number of gradients at the same amount of total compute. Whereas if you use a larger batch size, but the number of steps that you need to hit the loss doesn't go down, It just means that you're doing a lot more compute per step, but you'll end up taking as many steps as before, which is going to be slower than just using a smaller batch size. Even if the GPU utilization is not high, typically small batches will still be faster in absolute terms than larger batches. They'll just have like a low utilization relative. Okay. This varies between different tasks. For C410, like we said, it's something like 256, which is actually tiny. So if you have an A100, you can probably fit like batch sizes in the thousands and thousands. 256 is very small. Like even on an old GPU, like 256 easily fits, and the A100s, which have like many times more memory, can fit huge batches here, but it's not going to be efficient for ResNet 50 training on ImageNet, which is a much larger and more complicated data set. This like critical batch size where parallelization stops being more efficient is roughly 2 to the power of 13, which I think is 8K. Yeah, and for transformers, it's something else. It really just depends on the tasks that you're doing. The reason why this happens is that if you look at this picture kind of here, that as you increase your batch size, you're getting a better and better estimate of the gradient. But this which means that you can take larger step sizes, and hopefully this like larger step size will kind of give you the same benefit as smaller steps, as more steps with a smaller batch size. But this only helps up to a point, right? Like maybe you only need 256 samples roughly to get like a very good estimate of the gradient. Beyond that, yes, you get a marginally better estimate, but it won't really allow you to take like bigger step sizes. You already get the direction right. The step size is going to be limited by the curvature of the loss function, not by the accuracy of the gradient estimate. Okay. I hope this is somewhat clear. Yeah. Yeah, this is like an active, I would say, like research area a little bit. Like one estimate of it is that you compute the signal to noise ratio of your gradients. It's basically you measure the variance in the gradient estimate and you divide it. You measure the mean gradient with like a very large batch size, and you measure the variance of the estimate or like like per gradient sample roughly. This gives you a signal to noise ratio. You want the signal to noise ratio to be roughly 1. When it's around 1, you're pretty much at the critical batch size. So yeah, I guess, okay, you compute the true gradient, you use like lots of batches, then you compute the variance between different batches in the estimate. So yeah, you divide these two roughly where you're getting a ratio of 1. That's a rough estimate of the critical batch size. And this paper here actually describes this. But in practice, this critical batch size actually varies throughout training, which is annoying. And it depends on the learning rate that you're using and so on. So it's like, yeah, it'll give you some sort of like rough idea, but like I personally have seen this many times be off by a lot. Like for instance, in this kind of like nano GPT training that I do quite a bit, there it really seems that like the critical batch size is tiny, but like this estimate of the critical batch size is tiny, but in practice, these batch sizes still work fine.
Let's check 532, 256, and 128. Choose the best one.
Yeah, like the issue in practice is that you need to tune the hyperparameters for every batch size. So this is why like almost nobody does something like this, you know, because really behind this plot, you know, probably like thousands or you know, thousands of runs. Every point here is like, you know, they search like hundreds and hundreds of hyperparameter combinations, pick the best one, and there'll be lots of hyperparameter configurations that don't actually work for this batch size. So yeah, it's something that is good to be aware of, that, you know, nowadays, especially if you have a big GPU, you're training a small model, you know, that may just not be efficient overall. And especially, you know, using huge batch sizes that like completely, you know, fit within the GPU, it's not necessarily efficient. So if you're training, you know, kind of like, you know, real, you know, big networks that you know, people sort of like currently use for some sort of like, you know, production, then, you know, you can go with the biggest batch size that fits on your GPU and it'll probably be fine because the critical batch size is probably much larger. If you're training these kind of like, you know, toy problems, then yeah, it just doesn't work with like modern GPUs like that anymore. Yeah, onto the hyperparameters. So I still recommend this recipe that like I described in the intro. So R&W, this optimizer shown here, plus a cosine decay schedule with warm-up, which can be 5% by default. It also works fine with like large batches. But yeah, there are the hyperparameters actually change with batch size, and most of them have some sort of dependency on the batch size. The most important ones are the learning rate and potentially the weight decay. With larger batch sizes, you want larger learning rates because basically what you wanted with the larger batch size was to take a bigger step so that you have to take fewer steps overall. If you take the same step size, you know, you'll end up having to take just as many steps as before. You're just, you know, wasting your compute again. And with weight decay, it's a similar story. Weight decay is actually just like it's like a second learning rate that kind of scales your actual learning rate in some way. So in my recommendation here for this R&W optimizer would be to scale the learning rate roughly with the square root of the batch size, and same with weight decay. It's crucial that if you're anywhere close to the critical batch size, your momentum should be high, at least 0.9, probably higher, maybe 0.99, something like that. And instead, your second moment, which kind of normalizes your gradients or updates over time, can decrease. I don't know about that specifically. I would expect like a momentum of like 0.5, at least for like kind of, you know, optimization where you just have a fixed objective function to be quite, you know, meaningless. It's going to have a very minimal impact. But the issue with like GANs and reinforcement learning maybe is that your objective function keeps changing. So it's a much more complicated optimization problem. I honestly don't know, you know, what the best practices are there. But for image networks, for LLMs, something like that, like, yeah, this, you know, the loss function is fixed. It's not shifting over time in some weird way. Then, yeah, you want high momentum. And yeah, if you're using large batch sizes, like let's say for like nano GPT or something like this, if you use a default value, which I think is like 0.999, it stops performing well. You have to lower this value, otherwise your training doesn't work. Yeah, you get much worse losses. Okay, so that was the first portion. And yeah, I hope maybe I should speed up a little bit for the second part. But the second part is all about distributed training. So we've kind of seen, like with one GPU, what are the considerations? How do you achieve some efficiency? And now, okay, if we train larger tasks, one GPU is not going to be sufficient. You actually need to use many GPUs, otherwise it's going to take forever, or you may not even like fit the model on a single GPU anymore. Okay, and yep, so how do we efficiently train large models? The issue is that like with time, we have just been increasing and increasing the size of the models and the compute required, especially in the numbers of like parameters. We've gone from, you know, like maybe 2018, like 100 million parameters, which nowadays like considered kind of like a toy task, to, you know, like hundreds of billions of parameters. And the issue with this is that this no longer fits on a single GPU. Like we saw before, like a single GPU might have 80 gigabytes of memory, which, you know, you won't be able to fit like 170 billion values into those 80 gigs, and that's without any optimizer things or anything like that. So this poses system challenges. So for GPT-3 training, for example, like a V100 is an older GPU generation, but it takes roughly 300 GPU years to train it. So if you use one GPU, it's just, you know, you're going to be waiting forever. So in practice, you need to use, you know, hundreds at least, probably thousands for training to complete, even within like months. The memory issues also, even just to store the optimizer state for this, you need like 100 GPUs. And then we have issues with kind of communication between all of these GPUs. You have to have like high bandwidth. What I'm mostly going to be focusing on here is this paper that came out a few years ago called Megatron, which is studying like different ways of like parallelizing this problem to train these large models effectively. They go up to like 1 trillion parameters, which is like 5 times larger than GPT-3. Okay, and here's just a few more figures showing like the compute cost. So really, since the start of like deep learning, we've been increasing faster than this like these you know, basically then like hardware has been getting faster, so we've had to increasingly parallelize our training, and especially with these like large LLMs, you know, we jumped a few orders of magnitude compared to like deep learning, which is already on like a very rapidly increasing trajectory. The cost of training has also been increasing a lot. So here, if you want to train some, you know, state-of-the-art models, it's, you know, you're looking at like $10+ million for like a single training run, which of course means that like most people can't do this in practice. And, you know, some of the methods that we see here, you know, it's kind of interesting to know about, but, you know, in practice, most people actually never get to like use them at scale, because only a few companies can train these models. Yeah. Okay, so this is maybe a bit of a recap, but I hope you saw like transformers. Yeah. So this Megatron paper is about training like basically large transformer models, and a transformer consists of these like blocks that you should have seen before. So there's each block has a sub-block with attention, and another one which is like this MLP. So just a few matrix multiplications with a nonlinearity here. And then you just like stack all of these. And it's important to have this in mind, because the parallelization methods will to some degree depend on your model architecture. So we're going to be focusing on transformers here. Everyone uses mixed precision training if you want to train large scale models, because you could already see like how, you know, how much the cost to train them, how many flops you need. You want to be squeezing the performance out of the GPUs. So in practice, you need to store the weights, and you need to store a few other things like the momentum, the second moment for the optimizer. So overall, you're looking at roughly 20 bytes per parameter in the model. So if you have, you have 180 billion parameters, you multiply this by 20 to get the number of bytes that you need to store the optimizer state. Okay, in practice, this Megatron paper used a cluster, a supercomputer that was like one of the top ones back when it came out. The clusters are divided into nodes or servers. Each server has something like, here 8 GPUs. These 8 GPUs that are on a single server have very fast interconnects. They can communicate very fast. Like here, we saw that the memory bandwidth of these A100s is roughly 2000. So like the GPU bandwidth is roughly like 1/3 of this, which is still very high. And then it has to be communication between the nodes, but not as fast. So now you have kind of like this heterogeneous connectivity. Like some GPUs can talk to certain GPUs quite fast, but like some other GPUs will take much longer. And this will also affect how you kind of set up your parallelism. And in general, you can kind of divide the types of parallelism into 3. So here we are just considering the total compute that we need to do, let's say, for a forward pass through a model. And you can kind of view this as a cube. On one dimension, you have all the different layers that you need to process to get the output. On another one, you have the width of the network. So at every layer, you have like your many neurons. Each neuron is going to give you an output. And finally, you have the batch size. And on each of these 3 kind of like axes, you can divide the work that you need to do. So here for data parallel, we are allocating like 1 worker or 1 GPU to each chunk of the batch. Then instead of dividing the input data, we can also divide the model. And this is called model parallelism. There are 2 sort of important types. One is called tensor parallel. There we are really dividing the model along the width. So like 1 GPU is going to process certain neurons at every layer, let's say. Another one is going to process another chunk of the neurons and so on. And then finally, we have pipeline parallelism, which is dividing the layers between GPUs. Okay, so the first method and the most commonly used in practice, I would say, you are quite likely to use this at some point. The other ones, pipeline and tensor, maybe slightly less so. But here, like I said, we just divide the input samples between different workers. And what this means is that each GPU just does the same thing as a single GPU. It does a forward pass, it does a backward pass. Then each GPU is going to get a gradient. We are going to communicate these gradients between all the GPUs. Essentially, we are going to reduce them. We are going to take the sum of the gradients of each worker and send it to each worker. So in the end, it's called like an all reduce. So each worker contributes their local gradient. It gets back the sum of all gradients. And what this gives you is that each worker is going to end up with the same gradient as if it had done the entire batch itself. You do an optimizer update on each worker, and the weights will stay the same on each worker afterwards. This is nice. This is like the traditional way of doing sort of like large scale training in the era of like deep learning before like LLMs and so on. It has very nice scaling properties for if you just have a few GPUs. One trick that we do in practice is that when we're doing the backwards pass, we get gradients for the early layers before we compute. We get gradients for the later layers, like towards the end of the model, before we kind of backpropagate through the rest of the model, and we will start communicating these gradients that we already have as soon as we obtain them. while we are doing the rest of the backwards pass. So you can overlap this communication between the different workers and the backwards pass. And this means that like you often get quite small overhead from the communication. Yeah, and then if you have some like, you know, critical batch size to spare, you can even do like multiple, you know, forward and back passes, accumulate the gradient on each worker before like communicating the sum from each gradient, which will reduce your communication overhead even further, but it's only possible if your critical batch size is large. The weaknesses is basically you get no memory savings, and yeah, the critical batch size in the end is going to limit how far you can scale this. Yeah, this is like gradient accumulation. Peter, did you discuss it? No, okay. Yeah, essentially, sometimes you want to use a bigger batch on your GPU than you can actually fit in memory, and you can simulate this by just chunking the batch into smaller, we call them micro batches, doing a forward and backwards pass, and just end up like summing the gradients over like each of these like micro batches. You get the same gradient in the end as if you had done it on the entire batch at one time. This is important in practice if you want to replicate some papers that use more GPUs than you have access to. So quite typically, if you see some paper from like Google or something, they will use like, you know, a very large number of like devices for their training. But if you want to try to get something similar on like one GPU, even though it will take a lot longer, you can just use gradient accumulation. And this will allow you to use the same batch size for your optimizer as they did. So you don't have to change any of the height parameters. Whereas you could try to use a smaller batch size, but then you kind of have to figure out how to change the height parameters. And you can try to do this with some like, you know, like rules of thumb, or you can just use gradient accumulation to exactly replicate their optimization setup. And in practice, the way that you achieve this in PyTorch is essentially just by not zeroing the gradient until you've done a few like forward and back passes. Yeah, there is one minor detail here is that you divide your loss by the accumulation, because when you do these forward and back passes without zeroing this out, you are summing them up. And in practice, our loss functions are typically computed as a mean over the batches. So if you want to get a mean over a larger batch, you have to do this like extra division here, and then you'll get the same loss, the same gradients. Okay. There is a variant of this sort of like data parallel training that also gives you memory savings. This is not the main paper that like I'm discussing here, but it's good to know. These optimizers are called zero optimizers, or fully sharded data parallel, and in practice they're easier to use than the pipeline and the tensor parallelisms that we'll cover later. But essentially, the way that this works is that now, instead of like all GPUs storing all the model weights and all the optimizer states, each model weight, let's say for like one layer, is only stored on one GPU. And then during the forward pass, this one GPU is just going to send these weights to all the other GPUs, allowing them to process this layer. As soon as they process this layer, they're all going to delete it. So they only keep like the weights for one layer in memory at a time. You need to do this on the forward pass. You need those weights again for the backwards pass. So this like same GPU that has been assigned to these model weights is going to send them again to all the other workers to allow them to process the backwards pass in the same way. And this GPU will essentially also own the momentum that you need for these weights and the other optimizer things, and even the gradient. So it's just a nice way of sort of like sharding your optimizer state across many workers. This can give you quite significant savings. Let's say here that they are using an example where you have 7.5 billion parameters, and you're using 2 plus 2 plus 12, like 16 bytes per parameter for the optimizer state. So if you just do it naively with like standard distributed data parallel training, you need 120 gigabytes of memory to just store the model and the optimizer state for each on each GPU. If you do the sharding, you can get it down to 2 gigabytes, which means in practice, 120 gigabytes wouldn't fit on an A100. Like 2 gigabytes fits very well. Okay. The second, yeah.
Yeah, your 5 minutes video display how characters and models split and how to go from one to another from the whole thing.
Yeah, nice. And yeah, like maybe I should just emphasize, this is quite easy to use in practice. You can almost just like, we're going to show how we do the standard distributed data parallel. Like you can almost just like drop like a replacement in for it, and we'll kind of figure out like how to do this for you. Yeah, second parallelization method was splitting the model along the width. So if we view our model as these kind of like blocks, we're going to be splitting them like down the middle if we have 2 workers. The way this works can kind of be seen here. There are actually 2 ways of doing this, but they're all based on these like matrix multiplications. So if we multiply the matrix X by matrix A like this, we can get the same result by either splitting A into different rows and viewing it as a sum of 2 kind of like partial matrix multiplications. So if we want to do this here, like, one GPU would get like the upper half of A and the other one would get the lower half of A. They are going to process different chunks of the inputs as well. Yeah, sorry. Sorry, I can't hear you well. Yeah, you use this to save memory. Essentially by splitting the weight matrices like this. Now, like the first GPU only has to store half the matrix, the second GPU has to store the other half. So you save a factor of 2 in the memory. And yeah, there's a second way of doing this where we just, instead of splitting it, in an upper and lower portion, we split it into like a left and the right portion, and then you get different portions of the output features instead of like these like partial sums. And yeah, the benefits of doing this is reducing the memory requirements, and it's also just a nice way of like, you have more GPUs performing the same compute now. If you instead of like 1 GPU doing all of this, you can use 2 of them. So it allows you to use more compute power in this sense. It actually also allows you to save activation memory potentially, especially if you are doing this first thing here. Then like each GPU only needs to store like half the activations that it would have in the other case. The weaknesses are essentially this is very communication intense. So in practice, yeah, you don't want to divide this like into too many chunks, because this like communication versus compute scales poorly, and you typically would only use this within like a node where the GPUs have very fast interconnects. If you try to do this between, let's say, like servers or something like that, it typically is not a good idea. Okay, so in practice, this kind of tensor parallelism can be a little complicated. So in Megatron, they actually mix these 2 modes that we saw here to reduce the total computation overhead. So they start by basically the first mode here, like the partial sums, and then they follow it up by the partial features. on sort of like different chunks of the compute. So here, for the attention layer, they will split the heads between different GPUs. And for the output, like each GPU will only have like some neurons or some features of the output, but they will follow it up by doing without any communication to kind of like, like get the full state to each GPU. They'll follow it up by the other trick and get these like partial sums for this final matrix multiplication, and then they will sum it up. And so they only need to do like one kind of like reduce across the GPUs for this like subblock, and they use a similar trick on the other one. But also a bunch of other kind of complications with parallelism in general. Like sometimes you want to use the same random seeds between different GPUs. Sometimes you want to use different seeds, really depending on what you do. So there's a lot of like these kind of like extra details that you have to keep in mind here, because in the end, like each GPU is going to see the same state and then apply dropout. You have to use the same random seed. Otherwise, the state that is supposed to be identical between the GPUs is no longer identical. Okay. Yeah. Okay. Yeah. Okay. So the first question is like whether you need to do this yourself. And in practice, unless you're like a machine learning engineer working at a company that is doing this, probably not. Like you'll just take some framework where some other people have implemented this for you. For instance, you can just take the code for this like Megatron, and they will have implemented this for you in a nice way. Yeah, especially with like these tensor parallel methods, because they're quite specific to the model that you're using. You really have to think about like how you're going to do this. If you're just training a standard model, if somebody else has done it before, just use the code. That's yeah. Not the tensor parallel thing, the pipeline parallelism. I actually did a lot of. Sorry, Peter. Yeah, I would imagine it's kind of like just it looks like a massive headache to implement, honestly. Yeah, I think PyTorch now has some sort of like tensor parallel like modules in it. I have never seen anybody use them still. And I kind of imagine that like you still need to know a bunch about the model to actually use it effectively. Whereas the other, like the distributed data parallel, is roughly just you can plug that into any model and it'll work.
It's pretty easy to replace all simple layers with the power of evolutions.
Yeah.
But making some fancy stuff like transformer.
Yeah, I can imagine. Okay, the final method is this pipeline parallelism, where we divide the layers between each GPU. And the way that this kind of works in practice is that like you feed an input into like the first worker, it'll process it and eventually create an output. This output is going to be sent directly to the next worker. And you do this on the forward pass, then on the backwards pass, essentially the opposite happens. When you backpropagate, you start at the end worker, it'll backpropagate through itself and then deliver the gradient of the input to the previous worker. So it'll go, one way and then back the other way. The benefit of this is similar to like tensor parallelism. Essentially, you are saving memory, and you're kind of distributing. You're allocating more compute to the problem. A nice thing is that the communication here that is sent between workers can be relatively small. It depends on the batch size that you're using and like your model dimensions and so on. But like often, like the amount of communication is actually lower than for like other modes of training. The issue it's kind of like visualized here, and like what we are showing is essentially, okay, here we have different samples and different workers. So when we start a new kind of like, batch, the later workers have no work to do. Like, the later workers cannot do any work until the first worker has given them an input. And so this happens like when you start processing a batch, like the last worker is just going to wait until, like the third worker has finished its processing, which has to wait for the second worker and so on. So if you kind of like visualize with what each worker is doing at each time, it kind of looks like these plots. So worker one will start by processing a bunch of these like chunks of the mini batch, like micro batches. Then this worker will finish until it gets back gradients from the later workers. It'll also stall. So essentially, like each worker at different times is not going to be doing anything. So that's a computation like downside of this method. Another one which is important if you don't have these like sort of homogeneous models like transformers, if the layers are of like different widths or something like this, now you need to really carefully think about how you balance the throughput, because you can view this kind of like as an assembly line. Let's say, like, if there is one worker that is slower than everyone else, it's going to slow down the whole pipeline. Like, it's just going to create like a bottleneck, and yeah, you'll suffer on the utilization. Then there are more complications. For instance, like the different workers have to store a different amount of activations for the backwards pass, especially if you use slightly more efficient schemes like this. Or if you have microbatches that are sufficiently long that you like stop processing the backwards pass before you run out of microbatches, which I'll show on the next slide. And yeah, this is limited by the model depth. If you don't have many blocks, you can only like divide this into as many workers as you have blocks. Beyond that, it doesn't work. So yeah, people use these like tricks to get slightly more, slightly higher efficiency out of this. So instead of like doing all the forward at the same time, you try to like interleave this, and it'll basically save a bit of like activation memory for you. Then if you want to reduce this like pipeline bubbles that are here, you can make each worker process 2 chunks of the network. And yeah, this I'm not going to go into the details, but this basically works out. You will process each batch in less time than you did before, but at the cost of more communication. Okay. Then in practice, if you want to train these huge models, you can combine all of these, and that's what they did in Megatron. So each of these has like pros and cons, and in practice there is going to be some like optimal division between these 3 types. And in this Megatron paper, they explore this, and by sort of carefully crafting this like parallelization strategy, they get these like good results that scale to like very large models. Okay. Yeah, optimal mix. I think I'll also not go too deep into this, but basically the recommendations, what they do in the end is like this: in each node, like 8 GPUs, they use tensor parallelism. Then they will use pipeline parallelism just until you can fit the model. So you combine basically the pipeline and the tensor parallelism until you have enough GPUs that you can fit the model state. Then beyond that, to just speed up the compute, they'll do data parallelism on top of this. So those are the three axes. Then in practice, you need to store both the activations and the parameter memory. Like there is a nice trick for activation memory. You can basically, instead of storing all the activations that you saw on the forward pass that you need during the backwards pass, you can just store a subset of them and then recompute kind of like smaller chunks of the network at a time when you do the backwards pass. And this increases utilization. So this is a video of like how standard backpropagation is performed. So this is the forward pass, and the blue nodes means that you are storing memory basically for this kind of operation. They can be matrix multiplications or something like this. Then you will start the backwards pass, and now you're storing like kind of like gradients that are flowing in this direction. Here you have computed the output gradient for this, and you no longer needed the activations from the forward pass or the input gradients, because you've already computed like the gradient that you care about in the end, and you continue this, and you free up the memory as you go back. Gradient checkpointing works by like this essentially here. Okay, let me try to stop this one. Like this node is going to be designated as a checkpoint, which means that like this node before it, you just forget it. We're going to recompute it later. And the same for the other nodes that are not designed as checkpoints. So we just free up the memory. We need to store less memory at a time. Then during the backwards pass, we are going to do a little bit of forward pass here to get the activations that we need to process this portion of the backwards pass. So you kind of you repeat chunks of your forward pass during the backwards pass to have to keep less memory, less activations in memory at a given time. And essentially this allows them to scale up to like larger batch sizes. They fit larger batch sizes on the devices, which increases utilization. But this comes at a cost of slightly, you do have to do the recompute, so there's like a cost to that. But sometimes just being able to fit the larger batches on your GPU will kind of like pay for this extra recompute that you need to. And this is also kind of the idea behind flash attention. I don't know if that was covered, Peter. Okay, it's a similar trick, which like speeds up your attention computation, where you essentially trade more compute for less memory bandwidth, and overall it speeds up your training quite significantly. Okay, so some other optimizations that they're doing. When they do pipeline parallel, they have many network connections on each node. They can kind of like optimally assign them to kind of speed up this pipeline parallel communication. And they get some boost from this. But this kind of just shows like how low level you have to think about these things. You're really trying to optimize like every portion of this cluster that you're using to increase the throughput. And then these like fused operations that I mentioned before. So, these element-wise operations on GPUs are inefficient because you need to keep kind of like loading things in and out of memory, and you just do very little computation each time. Like sometimes you can combine a few operations into one. So you load the inputs once, you do a few operations, and then you write the final result back into memory. And this saves like a few round trips to the global memory, which just takes less time overall. And they're getting here like an 11% boost in the throughput by just combining a few operations like this. Yep. Yeah, it's typically not these like heavy operations like matrix multiplications. It's typically like, let's say if you had something like a sigmoid activation, which consists of like a few operations, right? You have to compute the exponent of the inputs. You have to like compute like 1 minus something divided, right? If you just write these operations in PyTorch, like it'll just do them like one by one. But instead, you can also just write like a kernel that does like computes the whole sigmoid based on the inputs without like keep sort of like reading things in and out of like the memory, the global memory. So yeah, it's typically these like small element-wise operations that are where the GPU is inefficient. Those are the ones that you want to fuse. Okay, and here is just a table of kind of like the results that they achieve here in Megatron, and they go up to like 1 trillion parameters, and they're actually getting 52% utilization on the GPUs, which means they are they're only a factor of 2 like max theoretically away from like what can be achieved, and that's with like all of these like communication overheads and everything like that. So like 50% utilization is very good, even on like on a single GPU. It's you should be relatively happy if you're somewhere around 50% utilization. It almost never goes up to 100% because for 100% you have to only be doing large scale matrix multiplications. That's the only thing. You just do that. You don't do anything else. No like activation functions, no gradient updates, anything like that. That's the only thing that can give you 100% utilization. So very impressive results. In practice, like I mentioned, you're probably not going to be using pipeline or tensor parallelism too much, but you will probably use this distributed data parallel for it. It's at least like way more likely than the other ones. And this is just how you set this up in PyTorch. And the important thing here is that you have multiple different processes. You can even have like different machines. Like on each machine, there is a different process that's running. We have to basically tell these processes how to find each other because they need to communicate. And there are a few different ways of doing this. One is just through like these environment variables in the operating system where you're specifying, some there's one process which we call the master process. That is kind of like the process that like coordinates everyone else. It's like so that process sets up all the communication and so on, but then it will also just train like any other process, but it has these like extra tasks. That's the master process. And when we start each of these processes, we basically have to tell them like, how do you find the master process, and what is your kind of like ID within this like group of like processes. So this ID is called the rank, and that sort of uniquely identifies each process that is partaking in this like distributed training. A local rank is if you have multiple GPUs on a single server. We specify the local rank just so it can pick the right GPU to use. The world size is just the total number of processes, the total number of GPUs that you're using. And the master address, which is the IP address of the master process, along with the port, just to tell all the other processes how to find it. In practice, you can do this manually, or there is a utility called torch run that basically takes all these arguments. It sets these variables for you, and then you just end with your sort of like training script where you can pass in other arguments. So this is how you would do it in practice, where you just copy and paste this between all the nodes that you want to start, let's say. making sure to specify the node rank here as well. Okay, so you have to do some setup. Then what you need to get right after that are a few things. One is typically that you want to be using a different seed for every worker. Like this is a common mistake where we are using an identical seed across the different workers. This will hurt you when you do some sort of like random operations like augmentations, something like that. You know, all the GPUs will be using the same dropout mask, the same random augmentations, you know, but you don't want that in practice. The second one is, in practice, you set a manual seed, you offset it by the rank of the process. The second one is the data, and for the same reason, you really don't want all the GPUs to be computing the gradients on the same data, right? That's useless. They'll give you the same gradients, but it's a very common kind of issue that people run into. So in practice, you want to split your data set with some class that is like designed to work with this little like distributed training schemes. And in Torch, this is this like distributed sampler that splits your data set. Then yeah, the final thing that you just need to do is you wrap your model into this. It's called distributed data parallel wrapper. And yeah, that's essentially it. You have to pass in the local rank here for some reasons that is like basically you want to give it the right GPU to use. I don't know why it couldn't figure this out from the process initialization. But after that, everything else is roughly the same as you had before. It's good to note now that like this backwards step here is going to be a synchronization point. So when this is called during the backwards pass, the GPUs will be communicating like gradients between them as you are doing the backwards pass. No GPU can move on. Like no worker can move beyond this point until like all of them have finished. This comes to the synchronization overhead of like these methods. Essentially, if one of the workers here is going to take longer for some reason, because maybe there is some other process running on that node or something like that, or you know, maybe like even the data loading is slow on that one because like the CPU is busy, somebody else is using the CPU, right? It's going to slow down all the workers again. So, and there are ways around this. What is it called? Like asynchronous and decentralized methods, where we no longer can like force all the GPUs to have the same, let's say, like optimized state at each point. So they can have like different, like essentially like each CPU can just like, you know, do a forward and backward pass. It will send its gradient somewhere. It'll have some like random points get gradients from other GPUs, but like we want to sort of like force them all to be like in sync with the same, you know, same model weights at every iterations and so on. So there are lots of methods like this. They are more computationally efficient. You can get high utilization by doing this. It removes overheads, but instead you have optimization issues. So using gradients that were computed on a different set of weights than the weights that you apply them to is has very tricky effects. And in practice, you know, you might see them. I don't recommend them for most training or like most jobs that you want to do. There might be some like, you know, odd use cases for them, but in general, you know, stick with synchronized training schemes. And yeah, that is it for the day on my side at least. Yep.
Google faces the
Questions?
Yes.